Okay, so this is lesson 7.2, reaction rates and stoichiometry. For this particular lesson, we're going to be using reciprocals and plugging into equations. So here it says, for reactions that have 1-to-1 ratios, meaning they're equimolar, such as the following: sodium chloride plus potassium hydroxide makes sodium hydroxide and potassium chloride. If you look at this, all of the coefficients are 1, and that means that it's equimolar, meaning that there's a 1-to-1 ratio. So we could set up a rate for all of these substances if this reaction undergoes completion. For example, here we're gonna say rate is equal to negative. We're gonna put a negative because sodium chloride is disappearing. So negative change in the concentration of NaCl with respect to time. And this is related to the other reactant. So we could set this equal to negative change in the concentration of KOH over time, over the change in time. And this is also related to the product, which is equal to positive change in the concentration of NaOH with respect to time. And again, this is related to this, which is equal to the change in the concentration of potassium chloride with respect to time. So all of these are related, and this is how you set up a rate for something that is equimolar. But now I'm asking, but what if the stoichiometric relationship is not 1-to-1? So for example, in this equation here, we have 2 moles of HI and 1 of this and 1 of that. So now it's a 2-to-1 ratio here and a 2-to-1 ratio there. So what does this mean? This means that 2 moles of HI disappear for every mole that these guys produce. The rate of disappearance is twice the rate of appearance of H2 or HI2. So how do we write this reaction rate? So the first thing you need to know is that we are not going to be using 2. Typically, we're used to that. So when we had a concentration, let's say this concentration of HI was 5 molar. We used to multiply that 5 by 2. And we can't do that anymore because we're not making HI. It's not an equilibrium reaction. Instead, we have to take the reciprocal. So it says here, if there are 2 moles of reactant here, we must take half of it with respect to the rate. So look, I know that sounds a little confusing, but this is how we set up the rate for the first equation. But for this equation, for that equation, what you're going to do is you're going to put rate is equal to, but instead of a 2, you're going to take the reciprocal. It's going to be half the concentration of HI with respect to time, which is equal to 1. You don't have to take the reciprocal 1 because it's going to be 1. So it's going to be positive, because it's being produced. You're making more of it, of the concentration of H2 with respect to time, which is equal to the change in concentration for I2 with respect to time. So here it's very similar. The only thing you need to know is that whenever you see a 2, take the reciprocal. If there's a 5 there, it's 1/5. If you see 10, it's 1/10. Okay, and let's say you're trying to find this, then you have to get rid of the half by multiplying by 2 to the other side. And we'll see an example right now, actually. So, let's do an example. So where it says rate in general rate, don't worry about that. Just write what I wrote and you'll be fine. Here it says, example 1, the following reaction occurs. 2O3 makes 3O2. How is the rate of ozone, this one, related to the rate of oxygen here? So when it's talking about related, it means how is it equivalent? So something equals something. So what I'm going to do is I'm going to write rate equals, and I'm going to put half. And it's negative because it's disappearing. Half of the change in the concentration of O3 with respect to time, okay, is equal to 1/3 of the change in the concentration of O2 with respect to time. The question is saying, how is the rate of ozone disappearing related to this? So we want this. We want to know how the disappearance of this is related to that. So what we do is we multiply by 2 because we want to get rid of half. And what you do to one side, you do to the other. So the rate is equal to the change in the concentration of ozone with respect to time, which is equal to 2 times 1/3, which is to 2/3, change in O2 with respect to time. So this is how it's all related. The disappearance of this is related by forming 2/3 of this. So now we're going to try another example, but this time with numbers. So here it says if the rate at which, okay, so I'm going to put this down. So it says, example 2 says if the rate, ooh, come on, right, okay, there it is. It says if the rate at which O2 appears is that 6, oh my goodness, stop. Is that, so the rate at which O2 appears is that, so that means 6 times 10 to the negative 5 molar concentration of O2 is appearing every second. What is the rate of O3 that is disappearing? So we want this. We want to find the amount of O3 that is disappearing. So what you do is you just plug it in. So after solving for this, you just plug it in. So the change in O3 with respect to time is equal to 2/3 times 6 times 10 to the negative 5 moles per second. And your answer is going to be 4 times 10 to the negative 5 moles per second. So that's how much O3 is disappearing at this rate. 4 times 10 to the negative 5 moles per second. You could put the negative sign in the front. You don't have to put it because it's implied. It's actually implied that it's going to be negative. So that's the way you do it, actually. Okay, so I want you guys to go ahead and try part A and then part B and see if you get it. Okay, now that you tried, let's go over part A first. So it says, the question says that we have N2O5 So the amount of N2O5 that's disappearing is this much. What is the rate of appearance of NO2? So we're going to look up here. NO2 has 4 moles. So we're going to take 1/4 of the change in the concentration of NO2 with respect to time, and that's going to equal what we have. So the only thing we have is N2O5. N2O5 has a 2 in the front, so we're going to put half the reciprocal of the change of N2O5 with respect to time. And again, we want this rate, so we have to multiply by 4. What you do to one side, you do to the other. So this is going to be 4/2, because half times 4 is negative 4/2, which is negative 2, right? And you just multiply that by the rate of that, which is 4.2 times 10 to the negative 4, which is 8.4 times 10 to the negative 4 molarity per second. And again, because this is appearing, it's the rate of appearance, this is going to be a positive number. Because N2O5 is disappearing, this is technically a negative, even though it's not shown up there. So that's why negative times negative, it's going to give you a positive number. So that's that. And then for part B, it says, what is O2? So O2 is right there. It's nice and easy here because there's no coefficient here that's not 1. So we don't have anything here in the front to get rid of, which is equal to what we have, which is that. So it's going to be negative half to the change in the concentration of this guy, which we could just straight out plug in, right? But let me just put it in generic form, just so you guys could see a little bit better. Right? And now I'm going to plug it in. So negative half times this, which is 4.2 times 10 to the negative 4 molarity per second, which is 2.1 times 10 to the negative 4 molarity per second. So that's how much oxygen is appearing from this substance right here, from the decomposition of that substance. Okay, so that's how you do it. For homework, I asked that students complete all of the problems that are related to this. So you guys check, if you were absent, please check in with one of your peers that was absent. If you don't have the handout, please have them send you a picture of it. I'll try my best to put it on Google Classroom soon, okay? But yeah, this is lesson 7.2.